Okay, hello. This is going to be the second set of examples for Chapter 2. This time I'm going to kind of talk about not just the examples from the book, but I'm going to talk about Section 2.8. I think if you haven't had calculus yet, 2.8 can be a little bit mysterious, and it doesn't have to be because it's really quite simple stuff. So let's look at what 2.8 talks about, and then we'll look at one of the examples from the book, and also one I kind of made up. Okay, so in 2.8, you're mainly using graphical analysis to look at position graphs, so graphs that have position versus time, like this one. And also, how does that relate to velocity graphs that have velocity versus time? One thing you'll notice that I did differently from the book, this is figure 225 in the book on page 36, is that I separated out the velocity part and I labeled that as the variable. Instead of like y, this axis is v. I would encourage you to label your graphs like that and then label what the type of quantity they are and the units off to the left or below. So this one's position, so I labeled it x because x stands for position. Let me also just tell you that sometimes in calculus and other classes, position is the variable s. So that could be labeled x, it could be labeled s, there's those different variables. Anyway, we didn't call it s in this case because our time units are in seconds and that would be confusing. Alright, so let's just talk about the main concepts in this section. They really aren't that bad, but for some of you they're a little new. And that's okay. The first one is that when you're talking about velocity, okay, velocity like this graph up here, let me just remove a couple of those things. Let's see. Doesn't want to let me do that. There we go. There we go. Okay, so when you're talking about velocity, graphs like this one, velocity can be considered as the slope of the position graph. So if you look at this graph over here and you consider the slope at any points, and what I mean is the slope of the tangent line, really. So we're really doing a little bit of calculus here. It's so much easier in calculus, and the proof for this is calculus, but that's okay. So if we think of the slope right here, it's a positive slope, so we know the velocity is positive. Likewise, along this entire curve, the tangent line is a positive slope, so the velocity of this object or particle is positive throughout 0 to 30 seconds. However, the velocity is less positive here than it is, for instance, at point A. So at point A, it's moving faster than it is at this 10-second time. So velocity is just the slope of the position graph. If you want to write that in symbols, you can write it as change in x over change in t, which is change in position, divided by change in time. That's just the slope of this graph. Likewise, if you want to talk about acceleration, acceleration is the slope of the velocity graph. So if you look at the velocity graph, between like points A and B, the slope is 0, so the acceleration is 0 between those two spots. Likewise, it's 0 between C and D, and the acceleration here is going to be negative because the slope of this part is negative. Acceleration over here is what? Should have said positive. Okay. So the third thing that we're going to look at in this video is displacement. We've talked about displacement a decent amount up to this point. Remember, it's kind of like the net distance traveled by an object or particle. In this case, if we have graphs, you can consider displacement as the area under the velocity. Now, of course, if you just have a position graph, like this one over here, the displacement can just be measured. So if you want to see how far the particle has traveled between A and B, you say, well, it looks like it's traveled about this much. So that would be the displacement. However, you can see that even on this graph, it's a little bit tricky to do it that way. So another way to do it between point A and B, if you wanted to find the displacement, is to think about the area under the velocity curve. you can look at how much area is accumulated in this area right here. And whatever that area is, it looks like that's 5 and it's 15 tall. So 5 times 15, that's how much the particle has been displaced, or how much it has traveled in net. So that's another way to figure out displacement. And I think in this example, it's actually easier. So very important. Again, the proof comes from calculus. If you had calculus, this should seem pretty natural. If you haven't, don't worry. You have a heads up, a leg up on any of those people who are in calculus, who haven't done it when you get there, haven't done physics. All right, so I thought let's just look at this a little bit more in depth in terms of the types of questions you might be asked. So the first question I said is, for both graphs, let's talk about what's the instantaneous velocity at 15 seconds. So it's easiest to do from the velocity graph because you just look at 15 seconds and say, the velocity is 15 meters per second. If you want to look over here at 15 seconds, the velocity, remember, is the slope. So we draw a slope, and then we'd have to think about how big that slope is. It looks like it's 1, but you've got to look at the scale on your graph. So it looks like it's going, and I can just estimate. We should get 15 though. But so between 10 and, let's see, that looks like it's about 20. So it runs 10. So we'll divide by 10. And it looks like it's gone up. See how hard this is to see. My graph's probably not perfect. So it looks like it goes how much up? From there to there, it looks like about 150 minus, what's that look like? Maybe 70. So that's, 80 over 10, which is 8. We should have gotten 15. So you can see how that's kind of just a rough estimate. But the key is that we use the slope of the tangent line for that instant velocity. All right, let's look at my next problem. What's the average velocity between 5 and 10 seconds? So between 5 and 10 seconds, that's here and here. On this curve, we can see it's about 5 and about 10. So the average of 5 and 10 is 7.5. If we go over here, let me erase that stuff. If we look on the position curve, the average velocity is the slope, not of the tangent line, but of the secant line. So between 5 seconds and 10 seconds, we'd find the slope of this line, which it runs by 5, and it looks like it changes by about, I don't know, what do you think? Maybe 30? I'm just estimating. So that's 6. Over here we said it was 7.5. They should be the same, but once again, kind of hard to see from this graph. So there's always choices. I hope by now you're realizing why knowing how to do this both ways is a little bit important. At least you're getting some idea. Okay, question 3 says, when is the velocity the greatest and when is it constant? If you have the velocity graph, when is the velocity the greatest? You're just looking for the highest spot. Well, it's not one time, is it? It's all this distance right here. Those times between 15 and 20 seconds produce the greatest velocity. If you look at this curve, between 15 and 20 seconds, it's steepest, which means the slope is steepest, so the velocity is greatest. Same conclusion. Where's the velocity constant? Well, it's constant also between 15 and 20 seconds, but it's also constant between 25 and 30 seconds. And you'd have to see a straight line, so really this should be straight. And really this should be straight too, shouldn't it? Okay. What was the acceleration at 5 and 17 seconds? So let's think about that. At 5 seconds, the acceleration, remember acceleration is the slope of the velocity graph. So at 5 seconds, the slope, we'd have to figure out the slope. It looks like it's rising 15, going over 15, it's 1. So the acceleration at 5 seconds is 1. And what's the units? 1 meter per acceleration, so second squared. and then they said 17 seconds. At 17 seconds, that's about right here. I look up at the velocity, and the acceleration is the slope. So the slope there is 0, so it's not accelerating at 17 seconds. It's 0 acceleration. Okay, how would you do average acceleration? I don't know, it depends. I guess if you wouldn't be looking at the slope of the tangent line, you'd be looking at the slope of the secant line. Number 5, how far did the particle travel between 15 and 25 seconds? So we could do that with either graph between 15 and 25 seconds. We'd have to trace it up and look at how much y value, or excuse me, I should say position value, x value has changed this time. That's going to be tricky to do. Let's just do it with a velocity graph. And I'm starting to sound cheesy. I apologize. So between what did it say? 15 and 25 seconds. So 15 seconds is right here. Should be straight. 25 seconds is right here. So I need to find this area. I think I'm going to split it into a rectangle and a trapezoid. So we said earlier this was 15 times 5. 15 times 4 is 60, so I think that's 75. Plus this trapezoid is 1/2. The bases are, looks like that one is about, that's tough to say, isn't it? Let's pretend that's at 10. You don't want to pretend in yours, but, and let's pretend, oh, that one's obviously 15. And the height is down here, so we're going to say that's 5. So that's 25 times 5, 125 times 1/2. What's 125 times 1/2? That is 12.5 plus 50, so 62.5. So that would be the displacement of the particle. So the units would be meters, because we're working in meters in both parts, you can see. Okay? Okay, so that's the first example. Let's see what else we have. Okay, I think I just had another example here. Let me zoom it a little bit. How do I zoom this guy? Huh. Well, I guess we'll just work with it like this. Just have to leave it like this time, sorry. Okay, so the problem in the book said a space probe accelerates uniformly from 50 meters per second to 150 meters per second. That takes 10 seconds. How far did it move in the first 6 seconds? So they did this by drawing a graph. So the this is a speed, you can see by the units, so it's a velocity. This is a velocity, so guess what? They drew a velocity graph. They started it at 50. Get a different color. They started it at 50, and they said 10 seconds later, here at 10, it was 150, and they just drew that line to connect them because they said it accelerates uniformly, which means it's a straight line. Now they're asking us how far did it go between 2 and 6 seconds. We just said that you can figure that out by finding the area under the velocity curve. So we trace it up to the velocity curve, and we try to find this area, which is again just a trapezoid. So we go 1/2. The first base looks like it's right here. Second base looks like it's up here. And it's how tall? Looks like it's 4 tall. This looks like it's clearly 100. I think I've got to be careful with this first one. So if we put 2 in there, how do we do that? Let's see what they said. So let's see. Oh, see, they got 110. got to be a little bit careful. Might be good to come up with the equation of the line if you're having trouble on that one. So how much is it changing every second? Or just think about the slope. Let me get rid of those things. So let's just think about the slope of this line. The slope of the line is this, right? So it goes up by 100, so the slope is 100 divided by it runs by 10. So that's a slope of 10. So from 0 to 2, it's going to go up by 20. So that means this is 70. And from 2 to 6, it's going to go up by 40. So that's going to be at 110. So now we are sure that we didn't make any mistakes, and we can find the area of that trapezoid by going 1/2, 110 for the first base, 70 for the second base, and multiplying by the height of 4, and we would get what they got, which is 360. And that would be meters, because once again we said that area under velocity is distance, and the distance here units were meters. Okay, that was not the best video, but I guess it'll have to do this time. So look for my problem examples. I'm going to post about 4 or 5 problem examples from this chapter, and I might go back and post 1 or 2 from the first chapter as well. Adios.